Hello, today we'll start our presentation going over basic ASM and then our program. So what is ASM? ASM stands for Assembly Language, and it is a low-level programming language used to write programs that interact directly with the hardware. Some key characteristics of basic ASM include the use of mnemonics like move and div, direct register manipulation, direct access to memory addresses, and the lack of abstraction. So why learn ASM? It's not a requirement for us as software developers, but it can be useful for 1. Understanding low-level concepts, like how instructions are executed step by step. 2. Having precise control of the hardware to maximize program performance and efficiency. And 3. Debugging, since we can directly inspect registers and memory. So how do I learn ASM? First, you should choose a specific CPU architecture that you're interested in, since ASM is CPU dependent, like any of these. 2. Set up a coding environment and get an assembler. 3. Learn syntax. And 4. Practice writing simple programs. So our ASM program is blackjack, but simplified. The goal of blackjack is to beat the dealer by having a hand value that is closer to 21 without going over 21. These are the card values. Jack, queen, and king count as 10, and ace in our program always count as 11. The rest of their cards count as its face value. When our program starts, the player will draw 2 cards, and then the sum of these 2 cards will be displayed to them. The player will keep drawing cards if the sum is less than 17. If the ending sum is between 17 and 21, then you win. But if the ending sum is over 21, then you lose. Then our program ends. This is the code for our program. In this run, you drew 3 cards, and the total is 17, so you won. Let me run it again so you have a losing situation. Yes, in this losing situation, you drew 3 cards, and the total exceeded 21, which means it's a bust and you lost. Now we will do a code walkthrough. First we will go through the game logic, and then we'll go through the helper functions. So in the first part, we have the .data section, which is used to declare and initialize data variables. From line 2 to 5, we define 4 strings used to display messages to the user using DB. DB stands for defined byte, and is used to allocate memory to store the entire string, including null terminated character, which is what the 0h means. The first message is a current card total, the second is a winning message, the third is a losing message, and the fourth shows which card you drew. In line 7, we define an array with the label R using DD. DD stands for defined double word. This is used to allocate memory to store the array, where each element is a 32-bit integer which takes up 4 bytes in memory. In the array, we have a list of all the possible card values. 2 to 10, Jack, Queen, and King has a value of 10, and Ace has a value of 11. Then we have the .text section. In line 10, we declared a global label called start, which marks the entry point of the program.
Thank you, Angela. The first thing we do is call our function random card, which generates a random card value from our card array. The call command transfers control of the code to a label, which in this case is random card. In random card, we first use RDTSC. RDTSC stands for read timestamp counter, which reads the current value of the timestamp counter, or the number of CPU clock cycles since the processor was reset, and stores that value in the general registers EDX and EAX as a 64-bit value. The first timestamp is always changing, and we use this to generate a random index for our array. Next, we mob the value 0 to EDX and 13 to ECX. By setting EDX to 0, we clear the EDX portion of RDTSC so that we have a 32-bit value in EAX that can be divisible by 13, another 32-bit value. The div instruction will divide the value in EAX, which has the other half of TSC, by ECX, which then stores the quotient in EAX and the remainder in EDX. We divide by 13 so we can get a remainder between 0 and 12, and that matches an index in our card array. We mob message 4 to EAX, and we call our sprint function, which Ruby will explain later, but simply put, it prints out message 4, which is you have drawn. Whenever we mob anything to another register, we replace whatever was in there originally. Next, we use the index stored in EDX to get a card value from the array. The word specifies a 32-bit 4-byte integer, which is what is in our array. R plus EDX times 4 finds the memory address of the value corresponding to the index, as each integer in the array is 4 bytes, and it stores the value in EAX. We then call iPrintLF, which prints the integer with line break, or line feed. I'll explain what this does later. The rec command then returns us to where we left off in the code. Next, we use the push command to store the value in EAX. Store the value in EAX, which is the card, on the stack. In assembly, the stack can store memory, much like the data structure, and has a push and pop command. The push command will store our value to the top of the stack, and pop will return the value at the top of the stack into a register. We call random card again to create another card value, and then push that card value to the stack as well. We move message 1 to EAX, which is current card total is, and call sprint to print it. Now we pop both cards off the stack, one to ECX and one to EAX, and we use the add command to add ECX to EAX and store the value in EAX. Finally, we use iPrintLF again to print the total card value. Next, Ruby will explain how our code keeps drawing cards.
We then go into the loop. The purpose of having this loop is to control the flow of the game, whether we end the game or continue drawing more cards based on the sum of the first two draws. If the sum exceeds 17, the program will print out the message and exit. If not, it will continue drawing more cards. Now let's check out the code. Since the sum is stored in the EAX register, we push the sum to the stack to save it for later. Then we compare the sum with the threshold 17 in line 30. Next line JGE stands for jump if greater than or equal. If yes, the code will jump to line 56, the win function. The win function copies the value of the winning message to EAX. Next line calls sprint to print out the winning message and then exit the program. If the sum is less than 17, the program will call the random card function again, and it will draw a new card. Line 36 pops the sum we stored in a stack and save in ECX. And since EAX stores the new number we just drew, line 37 adds up these two and save the new total in ECX. Line 38 to 39 call the sprint function to print out the string message, while 40 to 41 call the integer printing function to print out the sum number in the same line. Next, we compare the new sum number with 21. If the new sum is greater than 21, jump to the function above range, which basically prints out the losing message and exit the program. If not, jump back up to the front of the loop and start again. Now let's dive into the details of the helper function. The sprint function calculates the length of the string and prints them out accordingly. In the sprint function, the code begins by preserving the values of the EDX, ECX, and EAX onto the stack. Then line 85 calls the slam function. In the slam function, the code begins by preserving the value of the EBX onto the stack and copying the string message we are going to print from EAX to EBX. It then enters the loop of next char. Within this loop, the code compares the byte at the address in EAX with 0, which is the null terminator. If a null terminator is encountered, it means we are at the end of the string, so the program jumps out of the loop to the finished. Otherwise, it jumps back up and continues looping and increment the address in EAX. In the finished function, the code subtracts the initial address in EBX from the final address in EAX to calculate the length of the string and store the result in EAX. Next line, it restores the value of EBX and returns back to the sprint where we left off. Line 87 copies the string length from EAX to the EDX, and next pops the string message from the stack back to EAX. Line 90 copies the string message from EAX to ECX, and next line initializes EBX as the file descriptor for standard output. Line 92 then sets EAX to 4, which is the system call number for write, and invokes the system call with int ADH. This results in a string being printed to the console. Finally, the function pops and restores the value of ECX and EDX. Our function lprint_lf prints an integer with a new line character. It first calls iprint. Iprint will print the number without a new line. The first three lines are preserving the values of the registers of EAX, ECX, EDX by pushing them onto the stack. Next line initializes the ECX register to 0, serving as a counter for the number of bytes to be printed eventually. Victor will continue with the explanation of iprint_lf.
Thank you, Ruby. So we have set our counter ECX to 0. After that, we go to divide loop, where increment increases ECX by 1, which will be used for when we print the integers. We set EDX to 0 to hold the remainder later. We moff 10 to the register ESI and divide EAX, which holds the integer by ESI. By dividing by 10, EDX now holds the last digit of the number. So the number was 19. Dividing by 10 would mean EDX holds the remainder 9. 48 is then added to EDX to get the ASCII representation of the integer, and EDX is then pushed to the stack for storage. Then we compare EAX to 0. If it was 0, that means we have all the digits stored on the stack and we can go to the print loop. If not, we go back to the top of the divide loop and repeat it again. In print loop, we use decrement to decrease ECX by 1s. We move ESP, the stack pointer register, which points to the top of the stack, to EAX. We call sprint to print the number at the top of the stack. So if we had 19, then 1 would be on the top of the stack as it was added last and will be printed first. We pop that printed integer off the stack and store it in EAX. And then we compare ECX to 0. If it's not 0, that means there's still digits to print and we return to print loop. If it is 0, that means there are no more digits to print and we keep going. When we keep going, we're going to go pop EDX, ECX, and EAX back and restore the values and return to iPrintLF. Back at iPrintLF, we push EAX back into the stack to preserve it. We move 0AH to EAX, which is the ASCII character for a line feed or new line character. We push that onto the stack. We're then going to move ESP, the stack pointer register, to EAX so that we can call sprint again and print the line feed character. We then pop the line feed character off the stack and pop again to restore the original EAX value to its register. Finally, we return to the function and proceed with the code. So this function results in a number printed to the console with a new line character. Finally, we're going to look at the quit function. We use this when we win or bust. The quit function will mob EBX to 0, which is the return code for a successful termination of the program. We also mob EAX to 1, the system call for an exit. And then we invoke the system call, terminating the program. So that's the end of our presentation. Thank you for listening and have a good day.